in this video, we are going to talk about the new masterclass from Fast Society. It's a very long masterclass because it covers a lot of binary emulation and symbolic execution. You will have a lot of theory to follow in this masterclass, and once you finish, you will receive a PDF with all the content from the masterclass. It's important to understand that even if you don't have a lot of knowledge in binary emulation like the other courses will take, this will be a nice base for you to understand what the emulation is and how it works, and also from a very simple approach, which are Python scripts. You will not need to learn about C for the moment, or at least you will not need uh, a high understanding of C and C++, because in the other courses you will have to modify QEMU source code, which will be a little bit more complex. So this is a very gentle approach to all these complex topics, and in Fast Society we think that it will be good that if you want to do the other trainings and you are not really sure about them, do this one, and we think that you will have enough knowledge to join the others. As I said, what will this training cover? What this masterclass cover? So the core concepts, understanding the differences between what is emulation and what is symbolic execution, and how to use them in binary analysis. We will use practical tools that are well known by the professionals in the area of binary analysis, which are Unicorn, Quilling, Triton, and Miasm. And we will see some examples that can be useful for you to understand how to use them in CTF and in other real cases. So what are these tools that we will explore? So first of all, we have Unicorn Engine, which is a lightweight CPU emulation. This is based on QEMU, but it allows us to manipulate this emulation using Python, a very simple Python API. Quilling, it's built on top of Unicorn, and it extends these emulation capabilities, adding full system environment emulation. So we can access to files, we can provide hooks for DLLs or for functions from shared libraries in Linux, and it extends this emulation. Then we will jump to Triton, which is the first tool we will see in symbolic execution, which will allow us to emulate code, but then we will be able to solve some of the problems that we can find in some CTF, for example. But we can also use it to break some algorithms if we find them, for example, in malware analysis. We can break those algorithms that are used for encryption if those algorithms are not the standard ones. We can try to use symbolic execution together with SMT solvers in order to do this. And finally, we will briefly see about Miasm, which is another reverse engineering framework that which also does symbolic execution. And in this case, it contains an intermediate representation. So the symbolic execution is done over that intermediate representation. And also, in opposite to Triton, it allows us to do some of a static analysis together with this symbolic execution. So the objectives for the student are understanding when to use emulation and when to use symbolic execution. Also to control the APIs and how to use these tools, because they are usually very difficult to approach when you don't have any idea about emulation or about symbolic execution. Then applying these techniques to real binaries. So we will have binaries in the laboratory to use these tools. And finally, start using your own tools, so you can start writing your own tools. Uh, for the students, in the moment you want to use these tools, you will have a laboratory in fast society, together with the theory that you can follow one while you are while you are doing the exercises. So it's a hands-on practice on the topic. I hope you enjoy it. And now we will move to the example with Triton. Okay, so for this example, we will use a challenge that was released by X-Rays, the company that owns IDA Pro, the famous disassembler and decompiler, and it's called Free Madame de Mantignon. In this challenge, we have here that if we run it, we just see a very simple screen and a message that says you need to give the password as the argument. Okay, let's try giving the password. Challenge and test 1, 2, 3, 4, 5. So it says, oh, wrong place. You have to learn you have to look somewhere else. So it seems that our test 1, 2, 3, 4, 5 was not the correct password. We can use disassembler and decompiler as binary ninja. So while you can use IDA Pro, you can use Ghidra if you don't want to spend any money on it. In my case, because I'm starting to use Binary Ninja and I have this license, I will show you in Binary Ninja. This challenge was not very difficult because the code was not obfuscated and we just have a very simple main function. So in this very simple main function, we have the next code. We can see the pseudo C code, but I have to say that things like this with all the all the cast, sorry, are a little bit overwhelming. So I prefer the high level intermediate language. I think it's possible to remove those cast or from the view, but let's continue like this. So I already applied some analysis on it. And so as you can see here, if we provide one argument, at least one, the first argument is taken and saved in this user password, which is a char pointer. And then we have a password that is 0x19. I think we can display as decimal 25 size. So after that, we have that this password is set to 0. So all the buffer is set to 0. And finally, 24 bytes from the user password are copied to this buffer. What will this challenge do with the entered password? So what we'll see is that different mathematical operations are applied during this challenge. And in order to finally get the final flag, we will need to pass all of these checks, giving the correct input, giving the correct string as input. So here we have, for example, the offset 0x16 from the password. Here, word size is taken, so 2 bytes. Same for 0x10, same for 8. And then we had here aux, that is 0xe. So these mathematical operations are applied. So here we have an ADD, subtraction. This operation must give as result 0x1cd4. I agree that this operation, maybe it's not so complicated, and we can try to solve some parts of it using just a pen and a paper. But it is true that brute forcing all those possible values will be a little bit difficult. Same for the second check. So we moved here and we have a second check. It's pretty similar to the previous one, but using different offsets. So as we can see, what it's doing is for checking different parts of the password given by the user, the argument given by the user. It goes taking small parts from the string, casting them to integers of different sizes, and checking them with different constants. Here we have the second check. The third check, instead of using word size, it used keyword. So we have 8 bytes. So, for example, it checks that the password 0 and the password 0x10, those offsets using keywords, when you apply XOR over them, you have this result. So what we have, if we start checking all the other parts, so here we have the fourth check. I don't need to explain. You have here the comments. So in this case, you also have some shift left operation and shift right. What it's doing is taking those correct values, those values from the user, and checking if they are correct based on different mathematical operation and on different results from those mathematical operations. This is what in symbolic execution we will call constraints. So in symbolic execution, we will need that certain mathematical equation applied after, so applying those mathematical equation and given some constraints, we can provide those things to an SMT solver like the library C3, and we can ask the library for a model that solves those equations with those constraints. So in our case, the equations will be all of these mathematical operations that we have, and our constraints will be the values that those mathematical operations must be equal to. As I said, we can try to do that manually, or even we could try to take these operations and writing in the C3 syntax the different equations and providing them to C3 in order to solve all of them with the constraints. But what we will do is instead of doing manually, we will use Triton to emulate the code. Then we will need to know where we need to apply the constraints and where we need to get the AST, the abstract syntax tree of the execution. So what does it mean, this? Let's go to the first one, for example. Instead of checking it in high-level intermediate language, we will use the disassembly part. So after applying these operations, is one, and so on, we will have a comparison. Compare AAX with 0xD899. What we have to do is once we reach this point, we need to extract the abstract syntax tree from this register, from EAX, and that abstract syntax tree in Triton contains all the operations that affected to the value stored in EAX. With Triton, we will do something called concolic execution. That means we will provide concrete values like 0, 1, 2, 3, A, whatever, concrete value, but we will also treat those variables or those register or that memory as symbolic. So every time you Triton operates with those symbolic values, it will start creating an equation, an abstract symbolic tree that contains all the operations that have modified the data, that symbolic data. And then with that value, what we can do is to apply the constraint that all the operations must be the result of applying all those operations must be this. Okay, so with that, we will be able to extract a model which are all the values that can match that constraint. What happened that we can have many values that can provide those constraints. So here we will have one model, we could have another. We have to apply more constraints. Where do those constraints come from? From the other checks. What happens if we start saying, okay, you found a few values that can solve this equation and match this constraint, but I also want that those values can solve the next operations, the next mathematical operations with the other constraints. What we have is we have a big set of numbers. We reduce them applying constraints from the first check. So C3 try to look for a set of values that can solve that equation with that constraint. And once we start applying more constraints and more equations, we have that this set of numbers is becoming smaller until the point that we find that those set of numbers match exactly the string that can solve the challenge. So that's what we are going to do. Let's go into code in with the Triton API, a solver that can actually solve this challenge. We have to take a few things in consideration. We have to take from the disassembler where these comparisons are applied, because it's where we are going to extract the abstract syntax tree and apply the constraint. We will also need to take something in consideration, because Triton doesn't implement these SDL init, image init, and so on functions. Every time we find that one of these functions is going to be called, we just need to skip it from the emulation. We do not need it in this case. And also, if we skip it, we will not have any problem. We can provide our own implementation of some of the functions like string and copy. So we will provide our own implementation in order to say, okay, I'm going to copy the first argument, and the memory where I'm going to copy it will have a concrete value that will be a this number of times. And those memory values will also be symbolic. So every time you apply operations with it, just put it in the abstract syntax tree. So at the end, you can provide it to the SMT solver in order to have this solution. And finally, the last thing we have to take in consideration is that in this challenge, the pictures that we saw at the beginning, those are not in the memory directly. They are well, the one of grown data, this one is. But the picture that it's the solution, or that says that we have solved the challenge, this this picture is not directly in memory. So one thing we will do in order to improve this emulation is that every time we find a loop, we will just skip it. We do not need for this Triton script, we do not need the loop. We just need to skip it and continue with the emulation of the other instructions that are part of what it really matters, which is all the comparisons with the constant values. Okay, with those things in mind, we can start writing the script. So here I have a beam screen. And okay, we will start adding our lines from here. So user beam and Python 3. So we will always with Python 3. We can use this in case we want just to run it. Coding UTF-8. This is the common Python stuff that we add to our scripts. We will use the library string, and we can use time in order to check how long it takes to code to solve uh, this challenge. With Triton, we need to load manually the binaries, so we will use lief parser in order to get all the sections and all the parts from the elf file and all the bytes, so we can load those segments in Triton memory, and we can start working with them. And from Triton, import everything. Okay, so let's create a variable called target. What is this target? So it's the challenge itself. Then we will have some global settings. We will set symbolic to true, and concrete, it's just not symbolic. Then some memory mapping, some variables for memory mapping. So the PLT will be in 0x1. I have copied here the values, so I just need to make it easier for us. Let me see if I can copy this. So I just cannot copy, but no problem. Yes, let's set some address. Okay. Same for base arc. For the arguments of the program, this will be all of them memory addresses that we will use as bases for different parts of the memory. We have also a base for the stack, which will be 0x9 f f f f f f 0. That will be the base from our stack, because it will grow to the lower memory addresses. And also we will have some error value like 0, a, and 1, 2, 3, 5, 6, 7. Sure. So the mem address buffer, this will be where we will have the the place for the symbolic values. We will set it now to no. And the addresses of the conditionals that we will use. These addresses represent the places that we saw in the disassembler where the comparisons are done. So for example, for the first one, we'll have here, where does it start? Yeah, sorry. So yes, here it is. The comment is a little bit misleading, but it's okay, because this one is in 12 BF. So this address, for example, is the address of the first check. We will take from all the other checks. First check, first conditional. It's equal to 0x12bf. Second conditional, 0x12e0. Third conditional, 0x15. Fourth conditional, 0x1447. And the last one that will be where we will solve all the equations is 0x1492. Also, we will annotate the first loop and second loop addresses in order to skip them. First loop, it's in the 0x13CE, and second loop, it's in 0x1452. Okay, we will create a global method that will be useful for us to apply the solver check. So here's solver check. I have a typo. Oh yeah. So I have a typo here. First loop. Yeah. So the context that will be where all the Triton stuff is. The register where we will retrieve the AST, the value to check. A flag saying if we need to solve it right now. And also this show AST that we can use if we want to see how the AST from the equations are. We can set it to false, and if we want more information, we want to see how it looks, we can set it to true. This is just a debugging flag. So the first of all, we will need to get the AST from a register. Triton doesn't keep the AST in memory like a tree. It keeps pointers to different nodes. So if we want to print it, we need to unroll this AST. So we retrieve the get AST context. And then from the previous register AST, we do AST unroll. Right. And here we can print it. This will show us all the equations that affected to the value of the register. Okay, it's solved. We retrieve the path predicate. Get the path predicate. We will ask Triton for a model. Yes, with all the constraints, with everything that we added, and we will have this to store the values. So from the model, we will retrieve all the values for each index. So key values, k equal b. And finally, from here, we will retrieve the flag for k in sorted key values of keys, p equal key values, k, and the flag will be, yes, the char value of b get value. Once we have this, we can just say, okay, flag is this flag. Here the code is not linting, but I guess this is correct. Okay. The last thing we have to do is, because in the emulation, we want to keep running and properly execute the conditional, we will say, okay, context set concrete register value, register check value. And with this, once the comparison is done, we will be completely sure that this will work. In this case, in order to make it lighter for the video, we will not use much of the time, because this is just a demonstration video of what you can do if you if you do this training with the knowledge that you get from this training, what you can do for solving some of the challenges. This is the final script that I have. It contains many comments, so it's easier to understand. And well, as I said, this is the implementation of libc, which mostly it's used to set the values. So we get the register values from RDI, which is the counter of the arguments. We set the stack, so we have the stack, and we also set argc and argv. As I said, for argv, we provide first the name of the target, which is crack me. Oh, sorry, challenge. And as the second argument, 0x18 A's. So we will have this A, and finally 00. So this is the implementation of libc main, the start of libc. And we will store them in this structure, which I call custom relocations. Here we have the name of the symbol, the pointer to the function, and the third part of this list will be the real address to the real function. So when we are doing emulation, once we find that we are going to jump to this address, we will just run or hook instead of this one. As I said, in Triton, we cannot just start the binary and do the emulation. We have to load the binary in Triton memory. So we have the Triton context, and we have the leaf binary, which is the object from leaf that represents the elf file. And we go over the headers in order to look for those segments that contains pt load. So in this case, we just go over these segments looking for the physical size and virtual address, and we load all of them. If it's 0, it will not load anywhere. But in this case, those that has the virtual address, we will just set concrete memory area value in the virtual address, and we will load the content of that segment. We will need a make relocation. This is also another part of the scripts that you will usually see for Triton, which will be needed in order to properly get the address of that we previously talked about for the custom relocations. Why? Because once the elf binary is loaded, these functions will be loaded in specific addresses. We will need those addresses in order to know where we need to replace that call. For example, in quilling, when we are doing only emulation in quilling, this part is done automatically. We just need to say, okay, I want to hook this function from this library or this function with this method, with this Python method, and quilling will do all the dirty job for replacing it. And here is where it happens, the magic of hooking. So we will call this for every instruction that we emulate, and we will see that if the RIP, if the instruction pointer points to one of our custom relocations, which is this PC, this rel2 equals to PC. If we are calling one of the functions that we want to hook, just emulate it using the routine that we had. So we call it this function, providing context as the parameter, and we retrieve the state and the return value. If that state is symbolic, we will symbolize RAX. But in this case, as it is concrete, what we will not execute this part. We will just provide as the value, as the RAX value. Here it is. Sorry, the red value. So that means that if we return 0x18, the size of the string, we will assign that value to RAX. And if we want to make it symbolic, we will return that it's symbolic. So just symbolize the register. Then we will need to return to the point where we were running. So we retrieve from the stack the return address and we just hijack it in the instruction pointer. That's everything that we will need to do in Triton in order to properly emulate a binary and provide our own hooks. Finally, we have the emulate function, which is the most important one here. Why? Because, well, we will have this structure that contains all the conditional addresses as keys that we had. What do we have here? So for each conditional address, we will have the register that is checked with the comparison and the value that is compared with. This is, again, obtained from here, AX1CD4. AX1CD4. Once we have to do the comparison, we will call the solve method that we saw at the beginning. Also, we have the loop addresses. What is this structure? It contains the address of the loop and the address where we have to jump to avoid that loop. Easy peasy. Okay, so we will see another important point in Triton, which is how do we apply the emulation. So we have while PC, which is the address that will be provided here as parameter, while we have addresses, retrieve some opcodes from that area, from that address, from PC, retrieve 16 bytes, and generate an instruction. This is part of the Triton API. So, okay, as I said, if we find that we are in one of the calls to one of these functions, we will be here, or here, or here. Just hijack the value of RIP, retrieve its value, add 5, and continue the emulation loop. That means that we will skip this call and we will go to the next instruction. If it's one of the decryption loops, okay, just if we are in one of them, return the next address, assign it to PC, and again, continue. So as we can see, we can control really, we can make a very nice control of this emulation because we can just skip things. We will be emulating instruction by instruction, and this is what we are doing with Triton. Okay, but what happened if we are in one of these check register values? If it's the 5th conditional, it means that it's the last one. We will call solver check, providing the register, the final value, and also saying, okay, now I want you to solve all the equations that you created. Oh, sorry. Let me share the screen again because I think that you can only see Binary Ninja. Okay, sorry. So let's go back a little bit. It's from here where we, okay, so as I said, this is all the machinery that you need for hooking the handlers and setting all the libc and so on. And this is the emulate function. Here we have the most important part in Triton because here we will go instruction by instruction, emulating it and applying all the symbolic execution. This first structure that we have here, it contains the places where we have the conditional, the comparisons. And what do we have in these dictionary values? First, we have a register, which is the register that we use to compare in the instruction, and the value that we are going to compare with. Where do we take this part? So, for example, this first one, it's extracted from here. Is the comparison in the address. Then we have the register, which is EAX, and finally the value we compare with 0x1CD4. So same with the others. Then we have the loops that I commented at the beginning of the video, which are the first loop address and the second loop address. And the values of this dictionary are, where do we have to jump to skip those loops? Okay, so now we start in the emulation loop, which is the main part of all these functions. So while we have instructions, PC, the program counter that is provided as parameter for this function, retrieve 16 bytes, the opcode for generating an instruction, generate one instruction. We just need to create an object of the type instruction, providing PC and the opcodes. Then we have, if PC is one of these addresses, these are calls to this function. If we have not loaded the library, we will have that Triton will break because it doesn't know where these functions are or what these functions are. We just need to skip that call to that method, to that function. So we just retrieve the RIP, we add 5, and we skip the call. Then we need to avoid the decryption loops. If we find that PC is part of that dictionary, we retrieve the next address where we have to jump, and we assign it to program counter and continue. And now the key part of the symbolic execution process. If PC is one of these checks that we have to do, if it's not the fifth conditional, which means this else, just provide the context with the value 0, which is the register, and the value 1, which is the constant value that we are going to compare with. If it's the fifth one, and this is the last one, we provide all the information that we set, but also we will provide this flag saying, okay, now I want you to solve the equations with all the constraints, and I want you to give me a model, which means that we will retrieve the flag somehow. Okay, we have here how the process of the instruction is done, because we have to process the instructions. So we have applied all of this before the instruction is executed. If it's the type halt, that means that the program wants to go out. And also here we have one of the handlers. So in the moment we are going to apply some of the hooks that we created, we apply them here. Once we have run the instruction, we just need to retrieve RIP in order to get the next program counter. And now the run method, which is mostly the main that we have here, we will set concrete register values to RBP, the base pointer from the stack, and the stack pointer. We provide a base stack, which we saw at the beginning of the code, and we provide the same value. And then we use the time in order to see how long did it take to solve these problems. Then we call emulate, and as the entry point, we will just provide the binary entry point, because also we hooked libc start, so we will be able to process the ELF binary correctly. And the main set all the Triton stuff. This means we create a context, Triton context. We set some optimizations. We call lief to parse the binary in order to retrieve all the segments. We load the binary, apply the relocations, and finally we run it. So we will have the time of solving the challenge and the time of the whole analysis process. Let's run this Triton script and see if it's able to provide the solution. So this time I call it Triton solver. Oops. So it almost took no time. We had the loading process of the binary. We loaded the whole binary in memory. We applied relocations, and we created the entries for string and copy and libc star main. We said, okay, let's start running from this entry point address. Libc was hooked, and we set the arguments to these values. We found that they are calls to non-emulated functions, so we just skip them. And finally, we have the string copy, where we symbolize the user input. So this stack address is the user input. We have the first check, second check, third check. We skip the first loop, fourth check, we skip the second loop, and the last check. And a solution, we have flag equals free Madame de Mantignon. Emulation finished. The emulation time took 52.29 milliseconds, and the full analysis took 267 approach milliseconds. Let's try. I think we have it here. Before our challenge said, okay, this is the wrong place. This is not correct. Let's see with this input. Wow, it took a little bit longer to load, but we have the you have found me. We have been able to retrieve this flag using symbolic execution. So we were able to solve all this binary problem using Triton. So until here is the video to present this new masterclass in binary emulation versus symbolic execution. I hope you liked the video, and see you in the next one. Thank you.